This is part 9, quantization of the series, AI for Everyone. In our last video, we explored the inner workings of the GPT-2 small model. Let's now examine the memory requirements for training and inference of such models. Memory requirements for training. The GPT-2 small model has 124 million parameters, 768 dimensional vectors, a context size of 1,024 tokens, 12 attention heads. To estimate the memory needed for training, we also need to consider an important factor: batch size. Batch size is only relevant during training or fine-tuning and does not impact inference. On the screen, you can see the calculated values for training requirements. For a typical configuration, 2.86 gigabytes of RAM is required to train GPT-2 small. The total memory requirement depends on batch size and precision. Higher batch sizes increase memory usage. Precision also matters. FP32, 4 bytes per parameter, requires more memory than FP16, 2 bytes per parameter. Memory requirements for inference has a different memory footprint compared to training. During inference, we no longer need gradient memory, optimizer states, or activation memory. These are only relevant for training. Instead, we must account for the query, key, and value caches used in the transformer layers. For GPT-2 small, when using the full 1024 token context, inference requires only 755 megabytes of memory, much lower than training. Scaling up. Large models like GPT-4. Now let's consider larger models. For instance, GPT-4 is estimated to have around 1.76 trillion parameters, several orders of magnitude larger than GPT-2 small. One key difference between training and inference is the precision used. Training often uses higher precision, like FP32, 4 bytes per parameter, for accuracy. Inference can be optimized using lower precision, like FP16, 2 bytes per parameter, to save memory and improve efficiency. Due to these massive memory requirements, models like GPT-4 are impractical for most users to run locally, requiring specialized hardware like high-memory GPUs and TPUs available in cloud environments. Let's explore the impact of quantization on memory usage. We will cover how it works later, but for now, let's focus on its effect: reducing numerical precision, which directly lowers memory requirements. By default, training is conducted using FP32 precision, 4 bytes per parameter, which requires roughly 40 terabytes of memory during training. Now let's quantize it to FP16, 2 bytes per parameter, and observe its effect on memory. The requirement drops from 40 terabytes to 20 terabytes, a 50% reduction. If we further reduce it to INT 1 byte per parameter, the memory requirement decreases from 20 terabytes to approximately 11 terabytes. This demonstrates the effect of quantization. Not only does quantization reduce memory consumption, but it also speeds up the training process by enabling more efficient computations. A similar behavior occurs in inference. Let's examine it. For inference, quantization helps save memory and accelerate computations. Typically, inference is performed using FP16 precision, 2 bytes per parameter. When we further quantize from FP16, 2 bytes, to INT8, 1 byte, the memory requirement drops from 4 terabytes to 2 terabytes. As we saw the effect of quantization, let's now understand how quantization is achieved. You will also immediately realize the problems that arise due to quantization. This picture shows how various data types are represented at the bit level. Here you can see that FP32, also called full precision floating point, can store 23 bits for precision, whereas FP16 can only store 10, and BF16 can only store 7 of them. INT8, on the other hand, can only store values between -128 and 127. Hence, it is not shown in the picture. Let's look at this second picture. Now let's understand how quantization is done mathematically. Take an example where we want to quantize from FP32 to INT8. First, we need to find the minimum and maximum values in the FP32 version. From the simplified representation above, we can see that the lowest value in FP32 is -7.59, and the highest value is 10.8. The highest value in FP32 is mapped to the highest value in INT8, which is 127. Although the lowest FP32 value is negative 7.59, for symmetry reasons, we use negative 10.8, which is then mapped to the lowest INT8 value of negative 127. If you note, the chart uses negative 10.8 for the negative value, even though negative 7.59 is the actual lowest. Symmetric quantization often chooses the highest absolute value, here 10.8, and applies it to both sides, meaning the minimum is set to negative 10.8, even though the lowest observed value is negative 7.59. So in our case, the highest absolute value, AA, equals 10.8 is used for scaling calculations. This ensures equal scaling on both the positive and negative sides, even if the actual lowest FP32 value is not exactly negative 10.8. Now we need to find the scaling factor, for which the formula is shown on the screen. It reads as 127 divided by the highest absolute value, alpha, which is 10.8. So the value of S, which stands for the scaling factor, is 127 divided by 10.8, which comes out to be 11.76. What this means is that to get the INT8 equivalent of FP32, each FP32 value will be multiplied by 11.76 and rounded. For example, a value of 3.08 in FP32, when multiplied by 11.76 and rounded, will become 36 in the NT8 world. Since we know the scaling factor, we can also dequantize if needed. However, we will not be able to recover full precision. As you can see, it is not exactly the same as our original value, but quite close. If your use case can tolerate this kind of loss, quantization might be a good fit. Otherwise, it may not be suitable. Earlier, we mentioned that quantization has two benefits. It reduces the size of the parameter file and decreases the memory footprint. However, it also has another significant advantage. It speeds up the response time of large language models, LLMs. Let's understand why this happens. Look at this chart. It illustrates the effect of various data types on computational speed. FP32, single precision floating point. When using CUDA cores, it can perform 31.2 trillion floating point operations per second, TFLOPS. TF32, TensorFloat 32. If your graphics card has tensor cores and you enable them, you get at least double the speed, achieving 62.5 TFLOPS, even without explicit quantization. This happens at the hardware level automatically once you enable tensor cores in your code. BFO-AT16, brain floating point 16-bit. By using this format, you can achieve anywhere between 125 to 250 teraflops, leveraging tensor cores for acceleration. FP16, half-precision floating point. Similar to BFloat16, FP16 benefits from tensor core acceleration, providing 125 to 250 TFLOPS when enabled via code. ENT8, 8-bit integer precision. The real performance jump happens when quantizing to INT8, reaching an astounding 250 to 500 tera operations per second, tops. Now you may think, how do I know if the model I am using is quantized or not? There are several methods to determine if a model is quantized. One of them is model naming conventions. It's common for quantized models to include indicators in their file names, such as Q4, Q8, or INT8, signifying the bit precision used. For instance, a model named model Q40 suggests 4-bit quantization. Second method is about programmatic inspection. If you are using PyTorch, you can check for parameter data property as shown in the screenshot. In PyTorch, you can also check the quantization status as shown in the screenshot. In TensorFlow, you can check layer data types as shown in the screenshot. In ONX models, you can inspect node data type. Let us take a closer look at the performance of Llama 3.1 in comparison with its quantized counterpart. These performance evaluations have been conducted across 3 primary categories: chat-based interactions, instruction-following capabilities, and code generation tasks. By analyzing these benchmarks, we aim to understand the extent to which quantization affects the model's accuracy and efficiency in real-world applications. One of the critical benchmarks we will examine is the Arena Hard Auto V 0.1, which provides a comparative analysis of models across different quantization techniques. In the presented benchmark results, the left side of the graph, depicted in gray, represents the BF16 brain floating point 16-bit version of a 405 billion parameter model, whereas the right side, shown in blue, represents the same model but quantized to floating point 8-bit FP8 precision. Upon closer examination, it becomes evident that the performance of the FP8 quantized model is nearly identical to the BF16 model, with an accuracy metric of 99.25%. Similarly, an ENT8 quantized variant of the model has also been evaluated, and while there is a slight decline in accuracy, it still performs impressively well, achieving 95.84% accuracy. Key observations from the benchmark. Several crucial insights emerge from this comparative study. 1. Despite the reduction in bit precision, the quantized models exhibit remarkable accuracy retention when compared to their non-quantized versions of the same parameter size. This strongly suggests that quantization can be a viable technique to reduce model size and memory footprint while maintaining high performance. Second, smaller models within the same architecture family struggle significantly in performance. Simply using a smaller model does not necessarily lead to acceptable performance levels. For example, the 70 billion parameter model exhibits notably poor performance when compared to the 405 billion parameter version. The 8 billion parameter model falls into an unacceptable performance range, rendering it impractical for most real-world applications. This indicates that smaller parameter models severely degrade model effectiveness, making it clear that it is not a reliable solution for improving efficiency. This is due to small model having less parameter, which translate to less ability to learn and more susceptible to catastrophic forgetting. Now, there could be one exception where you create a small mode for specified task and train it on that specific task only. In such case, it will outperform the larger model both in accuracy, speed, and memory footprint. So there are niche areas for having small model that can run on edge devices, etc. Given these observations, researchers and engineers have recognized the need to explore techniques beyond creating smaller models which performs very poorly. While quantization is an effective method for reducing memory consumption and improving computational efficiency, it is not the only approach to achieving model compression while maintaining high performance. A word of caution: overall, in various testing, quantization seemed to be very promising, as we saw, but just be aware, if want your quantized model to do scientific simulation, large financial calculation, which requires floating points, do not use quantized model. Hi, I'm Naunihal Singh Sidhu, a Microsoft certified Azure Solutions architect with over 25 years of experience in IT, specializing in AI-driven transformation, enterprise architecture, big data solutions, and digital innovation.